Okay, so today, inshallah, we will start with lecture note 3. It's about probability and statistics. Okay, what's the importance of probability and statistics in the pattern recognition? Actually, what's the probability? Who can tell us what's the probability? Use your language only to describe it. Yes. Good. The chance of something to happen. Okay, but this probability, it's no one can know it, yes? For example, if you try to throw a coin and to find if it's tail or head, it's 50-50, yes? You cannot guess. After 2 times, 3 times, maybe. But after a while, you will find that there's a pattern in this probability. Okay? So this is the idea of most of probabilities theories here. Okay, I came late, and also students come late. Okay, so first part we will speak about the probability, then we will speak about the statistics. Okay, they are related together. I found that there is some problem with some pages in the lecture notes, but it's not a serious problem because of the PowerPoint is taken from the PowerPoint, so you will find in 1 or 2 slides some text over other text, but it's okay. So probability, it's the science of chance behavior, yes? What's the probability to get, if you have a bag and have some balls, what's the probability that you will get a red ball? Not red balls that drink, a red ball from this bag. This means what luckily, what's the chance to get a red ball? Maybe. Okay, you get a red ball or you get a ball. Another time, what's the chance? It will be changed depend on the first time you get a ball, yes? So we have some theories to speak about it. So usually it's unpredictable. You cannot predict which ball you will get or which fare from the die. If you throw the die, this cube that have some points on all the faces. So what's the chance to get one face? It's unpredictable. But if we said after throwing it 100 times, what's the chance to get 6 in the face? It's become more predictable because for the long run, for the experiment, you will have a predictable pattern. Same issue. Okay, we have a lake. This lake have only sea bass fish and salmon fish. What's the chance if I will get salmon or sea bass? Okay, it's 1-to-1, yes, 50-50. But it's depend on many things. After long run, you will find maybe almost you will get salmon or almost you will get sea bass. So each prediction, it's depend on the previous pattern for the prediction, okay? Not only the random theories that what you said, okay, it's 1/6 to get 6 fish, yes. But for the long run, you will find that the pattern will be more predictable, okay? Okay, so it's depend on the random. Okay? What's the meaning of the random? It's random. You are not certain. You are not sure about the output. Yes, but we have some regular distribution when we repeat this throw or this experiment. So we will have some repetition, especially if we repeat the, let's say, experiment for long time. Okay, I think this one, this slide have problem because we have two texts. So in the same place, so when we print it to PDF, you will get the two texts at the same point. But it's okay, it doesn't matter. We have many examples for the random experiments, like flipping the coin. You know the coin, like 1 lira, yes. On Kurush. I don't know why it still exists on Kurush, and you will go to the beam and they will give you on Kurush, base Kurush. I have a mountain in my house. I don't know what to do with this. Okay, so selecting a color from ball. This, by the way, we brought a question in the final exam, I think, about selecting a ball. Okay, or in the midterm, I don't remember, midterm or final. I send you, by the way, midterm and final about selecting a ball. Let me check. Why it's not clicking here? Oops, have many things to close. Oh, was here. No, it's not here. Final. I think not in the final also. I brought that question where I think in discrete mathematics, I brought it because we have number theory also. I think that a question in discrete mathematics. Discrete mathematics, yes. Final exam. Exam, I think this one. Not this one. Anyway, I will give you the question later. I forget where I put that question. Okay, rolling a die and picking a card from a deck means playing card, yes? All these examples for random experiments. Okay, And we have why it's written here. It's moving randomly, my mouse. I think it's very sensitive, the rule here. Okay, let's take example for something called relative frequency probabilities. Okay. Or probability of the outcome. When we observe for a long time, as I told you, a series of independent trial, we will have something called empirical data or pattern. Yes. We will see this patterns and example for it. Any experiment have something called the data sample, yes, or the set of samples. We name it usually S. Okay. Here, example. If you throw or flip a coin, for example, you will have, why the mouse is moving? Okay, I know now why. When I usually open the pen. When I have the pen, it will not move. I'm still in the mode of the hospital, not in the mode of the class. Fine, alhamdulillah. I just did test for my heart. Okay. So I found my heart empty. I went to hospital 3 days. Monday and Tuesday and today. First day I went to the doctor, go to the test, that effort test and something like this. Okay, then they put a device to check blood pressure. I slept with this device 24 hours. It's still red here. Then today I went there, they get the device, they get the treat for the blood pressure and everything. And I don't know what type of doctors. He never looked to my face. He never looked to the results. He never, okay, everything okay. I want to discuss with him. I want to understand some things. Okay. It's not about the language. He speaks English very well, and my wife speaks Turkish very well. So he rejects to speak in Turkish and in English and in any language. He don't want to speak with me. I'm taking blood pressure medicine, but I don't have blood pressure now. He said, no, continue. At the beginning, no need for blood pressure medicine. I told him, but I'm taking. You are taking? Okay, continue. I have the report with me, maybe 20 pages like this, but no benefits. He looked to the first page only, to the, like when you looked only to the abstract and you did not read the whole document. Same issue. So I will get another appointment with different doctor and different type. I will not go to heart or cardiology doctor. I will go to Dahili, yes, internal doctor. Because I have all the tests now. I only need a good doctor that can discuss with me, not only throw me. Not me, because me, he throw everyone. No one sit with this doctor. Just he have tens of patients. Okay, come, go. I don't know. Maybe if we cannot understand, it's okay. He takes the decision. But as a patient, I have to understand my situation. And anyway, alhamdulillah, my heart okay, alhamdulillah. Okay, I have problem with colon, but I'm playing, doing exercise and everything. I will not tell you what I'm playing. One of the students saw me. I think not here from programming. Okay, not one, a group of the students. Okay, let's return to our issue here. Relative frequency probabilities, it says that after the while, the chance to get the different choices of the experiments will be almost equal, yes? So we have two choices here when we throw the or flip the coin. Could be tail, could be face, yes? So it's here the probability to get how many times to get face, how many times to get tail, okay? So if we speak about the head or the face, the head, okay, how many times we will get head? At the beginning, if we throw 1 time, 5 times, 10 times, the probability to get the head or face, this one's tail, sorry, and this one's the head. You see here the probability is 0 because we get tail. Here's the probability, it's 0.5 because we get 1 time head, 1 time tail, and so on. Until when we have many times, when you flip 1,000 or 5,000 times, you will have almost same number or same trail of head and tail. So after a while, the pattern become like the probability of each choice, it's become almost equal. Okay. Of course, this experience because there is many issues that affect the result, like the patterns. Okay. We will speak about the probability of something depend on some probabilities or attributes because it will affect the probability also. For example, okay, if the probability to get the salmon fish and the sea bass, it's equal, but we can take some probability, some attributes like the lightness. And if the lightness more than 10, it will be almost sea bass. So you have equal probability here, but some attribute give you information here. So you will almost say, classify it as salmon or sea bass if you get lightness more than 10, and you have same probability for sea bass and salmon. Okay, I said that if the lightness more than, okay, more than 10, it's almost sea bass. Now, when we calculate the probability of what's the probability to get this fish, salmon or sea bass, we found that the probability 0.5. By the way, the probability will be between 0 and 1. 0, this means don't have any chance to get this attribute or item. 1 means you have 100 probability for sure this you get. 0.5 means 50-50. Okay, you get the fish to be salmon or sea bass, you have 0.5 probability. In this case, you come and look to the lightness. If the lightness 5, which one you will select? You will identify it as sea bass or salmon. Salmon, why? Because if the probability less than 10, it's almost salmon. But if it's greater than 10, as I said here, it's almost what? Sea bass. So probability plus some attributes or probability that we will select will make different with us. So if you have 15, the lightness, and you have the probability 0.5 for both, then it's almost sea bass. This is the idea here. Okay, to make model for the probability means describe the probabilities. You need first to know the size of the sample space, how many samples you have. Okay, if you have a die, you know the die, it's the cube that have, I'm not good in drawing, yes, that have some points here on each face. Okay. This is the die. What's the sample space to roll the die? What's the meaning of sample space? Means what's the possibilities that you have? We could have 1, we could have 2 points, we could have 3 points, yes, the face with the 3 points. We could have the face with 4 points and so on. So we have 6 different possibilities here. So the sample space here, what? 6. Okay. If we rolling 2 die, what's the sample space? 36. If you are rolling a coin, what's the sample space here? Why 36? Because some students. Because first one could be 1, second one, 1. First one, 1, second one, 2. First one, 1, second one, 3, and so on. If you take all the sample space, you will find that you have 36 possibilities. Okay, flipping a coin, what's the sample space? 2. Okay, flipping 2 coins, 4, and so on. Yes? Is it clear? Okay. So, the sample space, what's the different events or result from the experiments that we could have? Okay? And the probability is to take one event or one result from this sample space. Okay, so what's the probability for event 1? Here in this example. For example, you have 5 different balls and you will get 1 ball. Okay, what's the probability to get, for example, the red ball? If we have 5 different colors balls here. 1 to 5. So the probability for some event to happen, it's how many times this event repeated. Yes, we have this event one time here, divide by the S, which is the sample space. Yes. Another example, rolling a dice. Yes. What the probability to get even number? You need to know the event of get even number. It have how many event, or how many sub-event, or how many result? We have 2, 4, and 6. So we have 3 possibilities here. Yes. Okay. Rolling odd, also we have what? It's wrong here. 1, 3, 5. Okay. Rolling a prime number, also 3. Yes. Okay. So what's the probability number? What's the sample space? Here's a question. 1, 2, 3. This is sample space? No. We could have 1, we could have 2, we could have 3, 4, 5, 6. This is the 6 faces of the die. This one. So the different events that could happen, it's to have one of these 6 faces. So we have S equal 6. Yes. So to get the even number, we have 3 possibilities. So here the probability will be 3 over 3, which is how many space, which is 6. So the probability will be 0.5. Yes, this one equal 0.5. Here another example for a probability model for 2 dice. Okay, we are rolling 2 dice. We have 2, not 1. This all the possibilities. We could have 1 with 1, 1 with 2, 1 with 3, until 1 with 6, and 2 with 1. If you calculate here how many different results, you will have that it's 36. So what the events that we are looking, rolling even number twice. What's the even number? 2 with 2, 4 with 2, 6 with 2. Okay, here we have also 2 with 4, 4 with 4, 6 with 4, and we have, because this one different than this one. Yes, don't say it's same. Yes, 4 with 2 and 2 with 4. It's different here. Okay, what else? We have 6 with 6. 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, so it's 9 over 36. So what's the 9? The frequent of the event. What's the 36? It's the sample space. So this is the probability of getting even number on both dice if we are rolling 2 dice. Okay, here here arrange 52 card deck in zigzag, means take all the number from the same category, then from the second, and so on. Pick and S. Okay, what's the result here? 1, 2, 3, 4 out of 52. Okay, we already defined the probability. It's the event or the chance that some event will happen. And the ratio, or for this probability, it's number of ways a certain event can occur. Two means divided by the number of possible outcome. Number of possible outcome, what? We called it the sample space. And here, E, the event to occur. So E divided by S. So probability, this is a theory. Probability of some event, its number of favorable, means that choice, the one that I want to select, outcome, divided by number of possible outcome. We have many examples for this, like dice, a spinner, coin, deck of cards, even, odd number, alphabet, and so on. As I told you, all the probabilities is between 0 and 1, because it's number divided by another number. For E divided by S, it's always number, because E, it's always equal to S or less. E, it's less than or equal S, the event that you will select from the space. It could be equal to the space or smaller. For example, selecting a blue ball from a bag that have only blue balls. We have 100 blue balls in a bag, and we want to select one ball. What's the probability here? 1, because E, it's equal to S. We have 100 blue balls, and the total number of balls is 100. So 100 divided by 100, it's 1. This is the maximum probability. It's actually a certain, not a probability, because we don't have as a different event. We have only one item or one event here. So when we close to the 1, we close to the certainty. When we close to the 0, we close to the impossible or uncertainty. Okay? If it's 0 means it's impossible. Like what? Like selecting a red ball from a bag that have a green and a blue balls. What's the probability here? 0, because number of red balls in the bag is 0 divided by total number of balls. Doesn't matter what's the total. 0 divided by something will be 0. Okay. We have many examples. I don't want to waste the time here, mention all these examples. Okay. Like here, what the probability of rolling 4 number in the dice. To get 4 number, it's one event, one choice, yes? Divide by the sample, which is the different choices, which is 1, 2, 3, 4, until 6. So it's 1 by 6. Okay, to get even number, how many even number we have? 2, 4, 6, so it's a 3. And what's the total sample? It's 6, so 3 divided by 6. Okay. If we have, okay, if we're rolling a pair of dice, pair means 2 of dice, what's the probability to get a total of 5? So what's the probability to get a total of 5? In this case, how many different 5 we have? If we have 1 with 4, it's 5, yes? 3 with 2, 2 with 3, 4 with 1. We have any other choice for 5? Okay. When you have different choices like this, you can get the probability of first one plus the probability of second one plus the probability of third one plus the probability of fourth one and so on. So if the event have sub events, okay, so probability of the total event, it's equals the summation of the probability of the sub events. So the probability of rolling 5, it's the summation of probability to get 1, 4, 3, 2, 2, 3, and 4, 1. So you get this probability plus this one, plus this one, plus this one. So this one divided by 36 plus 1 divided by 36 plus 1 divided by 36. Of course, you can calculate it directly. Okay, to get 5, how many 1 we have? 4 divided by 36. So we have 4 divided by 36. Okay, another example. It's clear. If we speak about the green, it's 1 out of 4 different colors. So it's 1 out of 4. Get hit by flipping a coin. Okay, you have head and tail, so you have 2 possible outcome, and you need 1, which is the head. So 1 divided by 2. Same issue for to getting a heart. Okay, from a deck of cards. So how many different cards that have heart? We have 13. Yes, we have 13 heart. We have 13. What's this? It's called the spade or baston. I always confuse between this one and this one. One spade, one baston, but and this one diamond. This one I mixed between them. This one's a speed. This one baston. This one's a baston. I'm not good in playing cards. Not like you, Trex, Tarnib, and so on. I know. You have enough time to play cards. Who playing tricks here? How many of you know how to play tricks? Not to play, know how to play. Yes, yes. Not me. Okay. Every time you are fighting when you're playing tricks? Always. Again. Yes, especially if your teammate not good. You get what we called it, the king or what? And the queen, and you fly to the... Okay, so I don't want to waste your time for some concepts here. By the way, in this course, we have many concepts, but we don't care about all the concepts here. So if some concepts, it's important for the exam matter, because I know most of the students just care about the exam, I will tell you that this one, it's important, or something like this. This doesn't mean you will not understand the others. You have to understand the others. Okay, we mentioned all this one. Okay, this one important, the complementary events. Okay, complementary events. In some cases, it's difficult to know the probability of the event itself or to calculate it. And it's much easier to calculate the complementary events. If you have two events, okay, means if you have two events and the probability of one event and its opposite means a complementary, usually we mention it as dash, or we have this quotation on it, okay? So dash means this event, it's complementary for the E event. So E dash means this event, it's complementary for E event, means it's completed. If you have 30% probability to get E, this means you have 70% to get E dash, okay? So usually the summation of the probability for some event, and it's always, not usually, and its complement will equal 1. So in some cases, it's difficult to get the probability of event E. So what we will do, we will calculate the probability of the complement and then calculate 1 minus this probability of the complement. Then you will get the probability of the event itself. Okay. So example, you said, okay, if I can calculate the probability of E dash, then why it's much easier than in some cases to calculate the probability of E. For example, this one, if we have a sequence of 5 bits, okay, randomly generated. So this 5 bits could be, anyone could be 0 or 1, yes? So you could have 0, 0, 0, 0, 0. You could have 1, 0, 0, 0, 0, 0, 1, 0. If you want to calculate the probability like this, it will be a very huge number, yes? So what is the probability that at least one of these bits is 0? Calculate it. It's have a lot of calculation, yes? I need at least 1. Could be all 0, could be 4 zeros, could be 3 zeros, and the position of the zeros, and so on. Yes, you need calculation. We take it in discrete mathematics, by the way, how to calculate it. But why all this? What's the opposite of get one, at least 1 0? No zero. What's the possibilities of no zero? Only if I have 1 1 1 1 1. Yes? So what's the possibility or the event to get non-zero? It's 1. What's the probability to get 1 1 1? It's 1 divided by the sample. What's the sample? The different sequence of bits. What's the different sequence of bits? Every bit could be 0 or 1. Yes? And we have 5 different bits, so it's 2 power 5. So the different possibilities is 32. How many different sequences of bits? Only one of them is have 1 1 1 1. Yes, so 1 divided by 32. This is the probability of the complement. What do you need? Probability of the event. So it's equal 1 minus this one. So it's 31 divided by 32 because it's equal, this one equal 1 minus the probability of E dash. Okay, if one of you did not take discrete mathematics yet, and you return to discrete mathematics, don't write it like this. Use the discrete mathematics rules, okay? As you can see, most of or many of my courses depend on mathematics, yes. I was liking mathematics. I was one of the best students in my university in mathematics. Actually, I was planning to enter mathematics, but it's in my country, it does not have a future, yes. Just a teacher for mathematics. That's why I entered computer science. Then I could not, let's say, the jobs that days in my country, it's not too many jobs. So I went to Jordan, complete my master, then return, start my job as a lecturer, give. So I start first lecture when I was 25. I give in the university first. Yes, younger than you. I remember first day, first lecture. The smallest students, or the youngest, not the smallest, because it's small about the size. The youngest students was 45, something like this. It was open university, so most of the students not young. Yes. Anyway, we have something else. So we take the probabilities now and the probabilities for the complete complementary and the conditional probabilities. I mentioned it when I mentioned the CBAS and I mentioned the lightness and so on. Okay. Usually, when you pick, for example, a ball from a bag, you have 5 balls, 2, I don't want to say red, let's say green, and 3 blue. What's the probability to get in the second select from the bag a blue ball? Okay, it was easy if you said from the first select, yes? What's the probability to get the blue ball? What's the probability from the first time to get the blue ball? I told you, we have, let's say, blue and black. We have a bag. We need another color. Okay. We have a bag, a box, anything that have 5 balls. 2 black balls and three blue balls. What's the probability to get a blue ball? What's the space? 5 balls. Yes. What's the even for the blue? 1, 2, 3. 3 divided by 5. It's easy. Okay. What's the probability to get a blue ball in the second select? Not in the first select. 2, why 2? Why 3? It's depend on the first select. If the first time you select, if the first ball selected was black, then the second select, what's the probability in the second select to get the blue? 3 out of 4. But if the first ball was blue, it's become 2 out of 4. We name this conditional probability. So the probability to get some event here depend on the other events. The probability of the first ball, if it's black or a blue. We could use many things to solve the conditional probability problems, like, for example, tree diagram. For example, in a tree diagram, you will say, okay, we have first select. If it's black, we have what? 3 out of 4. The probability to get the blue in the second chance, yes? And if it's the first select, if it was the blue, then the probability for the second select or bet to be blue, it will be 2 out 4, because we already pick one blue at the first time. This is the meaning of using tree diagram. We could use formulas. Of course, we want to use formulas in the computer. We could use Venn diagram. You know Venn diagram? Of course, if you have to, or tables, or many things like this. How we write it in the formula like this. Probability of A depend on B. So for in our example, the probability of get a blue depend on first select was a blue. Probability of get a blue depend on first select was black. So we have 2 different choices there. We write it like this. So probability of get some event depend on previous event or given a previous event or some of previous probabilities that you get it. So we name this conditional probability. So we need to calculate probability of A, but we have condition B. Okay, given B or given condition B. Okay, let's check this example. In this example, okay, this data set of type of cars about petrol consumption, how much petrol it's used. For example, in 1 week, in 1 month, doesn't matter for us. Okay, because all the time will be same. So owned by 100 people. So this 100 people, we have male and females people. This the cars, this low consumption, medium, high. So as for the male, how many male car, not the car, the people who drive the car, male, how many one we have? Let's calculate. It's 33 plus 12, it's 45, so it's 52. This one will be 48. 23, 21, so 24 plus 4, 48. So the total, it's 100 car. We need to select one person at random way. So we will set L if it's low, M if it's medium rated, H if it's high. Here, male, and F for female. Let's see. Okay. One person is select at random, blah, blah. Okay. Let's calculate this different probabilities. Probability of get L. L means the person own a low rated car. This means low. What's the probability of selecting a car? It will be low rated car. 35. 35. Only 35. We said the probability will be less than 1. Yes? Between 0 and 1. So it's number of low, number of L, which is 12 plus 23, it's 35. So number of low, which is 35, divided by the total number, which is 100. Okay. What's the probability here to get female and low? Female and low, this one over what? And another question before you know over what? Female, given that the car is low. Okay, so female and low, this one. So it's 23 over the sample. Some people will say it's over the 48, and it's wrong. I never told you that the sample all is female. We still selecting from the total cars. Yes, I give you information it's female. No. Okay. And if you said over 35, also it's wrong, because I never told you that The cars only low consumption cars. I need female with low consumption from the cars, the total cars. So it's divided by 100. Okay. Female given low. Okay. Who guess? Female. Female what? Okay. Here you have to see this one. Okay, first of all, we have the summation, 35. We calculate it 35 over 100. We calculate this one. Okay. In this one, it's the probability of selecting a female given that the car is low rated. So what's the sample? Oh, Max, even I mentioned it here, yes, but you did not focus. I told you, F giving L. Giving L means I give you that the car for sure it's low rated. So what's the sample now? 35, yes. So only the low rated car, 35. Okay. What's the probability then? It's 23 over 35. Yes. So female and low 23. But the problem was with what? With the sample size. When I said F giving L, so the sample size become only the low rated car. Okay, this is the difference between F giving L, F and L. Here and L, I did not change the sample. The sample is still the total sample. But here I said, no, I give you that the car for sure, it's low rated car. You still need to check from this low rated car. So our job, all job, and don't confuse. Some people will calculate the female, then divide it into the rated car. Who told you? When I said low rated, then all my job in this column only. So how many female in this column? 23 divided on the total, which is 35. This is the probability of get female giving that the car is low rated car. Okay. This one, we will take a theory for it. Later, we name it Bayesian or Bayesian. Bayesian means poison, yes. You take it, you die. Theory. Okay, it's come from here. That the probability of F and L, it's equal the probability of F giving L multiplied by the probability of L. This theory, it's very usable. We will take many examples later for it. We name it conditional probability theory, yes? So probability of F and L, it's the probability of F giving L multiplied by probability of L. Okay, so Bayesian or Bayesian or Bayesian, doesn't matter, decision theory. It's one of the important theory in the static. It's taking something called the cost. We mentioned the cost last time when we mentioned the pattern recognition example for the Salomon and Seabass. Yes, we said if we cannot guess is it Salomon or Seabass, we have to look to the cost. So here probability for something given the cost. So it's a start to take the cost in our probability. Okay. We will mention the theory later. We will not take it now. Okay. I will take the attendance. Is it finished the time now? It's finished on 12 or what? We will take it at the 12. Let me continue, because if I stop for the attendance, we still have just a few slides. Let me check. I will be faster a little bit. Okay. Okay. So using this theory, we will study the probability of some events to happen depend on the cost, okay, or given the cost. So it's all about minimizing the risk by taking the costs into our mind here, okay. So if we have W, it's some random variable. For example, here we have W1. It's to have a CPass. W2 is to have Solomon in our previous example. So probability of getting CPass, we write it probability of W1, probability of giving Solomon. Okay. So let's take this example. So state of nature means what we have in the state, in the what we called it sample state. So imagine that we have only Solomon and Seabass. So we have two state of nature here, W1 and W2. Okay. The probability of these issues is come from experience. Yes. You will bring a fisherman and told him, if I start fishing here, what's the probability that I will get a sea bass or a salmon fish? It's come from experience. So we name it prior probability, yes? So from this prior probability, we can guess what the next fish will be. Okay, we will give examples tomorrow. Let's try to finish here. So usually, if you have equal probability, then probability of W1 equal W2. And if you have only two items or two types of fish, then the probability of getting sea bass is plus probability of getting salmon, it's equal 1. We know these issues. So how to write it? We write it like this. Our decision, if, okay, this fish, is it salmon or sea bass? to decide this, to decide if it will be W1, what's the meaning of W1? Seabass, W2, salmon. Okay, so that fish that I select will be sea bass W1 if the probability of W1 is greater than the probability of W2. Because this minimize what? Minimize the risk. I don't know. I select this one and I want to decide without looking to it. Is it sea bass or salmon? If I know that in most of the time, it will be what? Sea bass. So the probability of sea bass more than the probability of salmon, then I will say directly what? It's sea bass. Of course, you have some risk. If this probability, for example, 90% or 0.9, and this probability 0.1, then when I said this one sea bass, what's the risk here? What's the cost? 0.1. Yes? Because I know that 0.9 means most of the time it's probably will be sea bass. Then I said sea bass because there is 0.1. If it's 0.7, this one will be 0.3. So if I said this sea bass, what's the risk? 0.3. Yes? So this is the idea here. So what's the error or the risk for my probability? It's the minimum between probability of W1, probability of W2 from this theory. Okay, we said otherwise W1. So if a probability of W1, it's equal 0.2. Probability of W2, it's equal 0.8. Okay, I select a fish. Is this salmon or sea bass? I should select. I should say salmon. Why? Because otherwise, which is probability of W2, it's greater, and W2, it's the salmon, yes? Yes, so why I select it's a salmon? Because the probability of error here, it's the minimum, so I minimize the error. I take, it will be probability of W1. So when I select this as a salmon, the probability of error, it's equal 0.2. But if I select it as sea bass, means W2, then the error become 0.8, yes? Why? Because I did not follow this theory. So we have to follow this theory to minimize the error, because the error becomes a minimum between W1 and W2. So this theory is a decision making using this theory, minimize the error. To minimize the error more, we need to use the conditional probabilities. So not only the probabilities, and we take some probabilities or attributes about this event. So when we start to take attributes about the event, we minimize the error, we minimize the risk. Now we know that, okay, probability of Salmon, for example, 0.6, and the probability of sea bass 0.4. But when we take some condition, for example, the lightness, the width, the length, then the probability will change because also our space changes. Like this example, in this example, this, which one? This one. Okay. Our space become here. When we set the lightness, for example, greater than 10, then I will not look to the all fish. I will look to when the sample, we have the lightness more than 10. In this area, the most probability or the probability will be changed. So in some condition, the probability will be more accurate if I have some conditional probabilities. Okay, so we write it like this. So it's a probability of X giving W. Okay. For example, this example, consider it the lightness. So, okay. So if X is the lightness, I need the probability of W or X giving W or W giving X. Doesn't matter. Is it when I said the lightness is okay 11 or 11.5. So if you look here, 11.5. So we have more probabilities to be W2, not W1. Yes, because W1 it's 0.15, W2. Of course, this shape is come from some real data because we have different type of fish, not only salmon and sea bass. But if we consider only salmon and sea bass, it will range from 0 to 1 usually, yes? Okay, so this will be selected as W2. But if you are here, for example, the lightness 14, so your space become here. So it will be almost W1. So this WI, is it W1 or W2? It must be W1 to be in this area, and it W2, sorry, and to be in this area, it's almost W1. We will take more theories and more examples about this, inshallah, next time. Let me just take the attendance, okay?